Hi everyone, welcome to HORIBA webinar. My name is Kiwan Park and I'm going to talk about piezo particles today. And here's the agenda. First, we're going to talk about some fun facts regarding piezo particles. Second, we'll talk about the fundamentals. And we'll also look into the real-world applications as well and the hows of how piezo particles are manufactured. Specifically for lead zirconate titanate, also known as PZT, and then why the particle sizing is so important for this manufacturing process, and hopefully we'll have a Q&A session at the end. So some fun facts. Piezo is a word derived from the Greek word piezein, which means to squeeze or press. It's pronounced piezo. It has nothing to do with the pie, unfortunately. I know there's a word pie in there, but yeah, it has nothing to do with it. So piezoelectricity was discovered in 1880 by French physicists Jacques and Pierre Curie. So if you guys are familiar with the Curie family, radioactivity was discovered by Marie Curie, Pierre Curie's wife. So the Curie family, they hold 5 total Nobel Prizes within their family. So this is obviously a very illustrious family that has contributed a lot to science. So what are some fundamentals of piezoelectricity? So think of it as when you press these piezo particles or you stress these particles, it starts generating electricity, or vice versa. If you apply electricity, these piezo particles will press and stress. So pretty much what it is when you press piezoelectric current, it kind of gives electricity, and then inverse piezoelectric current is when you stress it. It also provides some electricity as well. Then if you kind of go back and forth between direct and inverse continuously, we also call that cyclical. So in short, when you have a piezo particle kind of vibrating or moving, then you will generate electricity. And then when you apply electricity to these piezo particles will start vibrating or start moving between the press and the stress. So that's the basic fundamentals of piezoelectricity. So how are these piezoelectricity particles are used in the real world? The one application we can look into is the dry powder inhaler. So this dry powder inhaler is much better and much easier and much less irritant to use compared to the meter dose inhaler. If you ever use the meter dose inhaler, it's the inhaler that you have to hold upside down and press it, and you inhale it. Unfortunately, the meter dose inhaler, it doesn't control the amount of powders that well, and then it doesn't really deagglomerate the APIs or active pharmaceutical ingredients. So people had a lot of complaints about it. But this new dry powder inhaler makes it much easier, much less irritant to use. So how does this work? So when you use this inhaler, it has a piezo actuator in the inhaler. So what it does is, as soon as you try to activate this inhaler and try to inhale this powder or API, what it does is it has a small tiny electricity that actually activates the piezo actuator, and that actuator is starts vibrating, and then that vibration deagglomerate these APIs in this inhaler, and then it controls the amount that you inhale, and also lowers the irritation because the particles are much smaller after the deagglomeration, so it's much easier to inhale. So this is one of the examples or one of the applications that's out there that is using piezo crystal or piezo metal. The other application we can also look at is the ultrasound. So if you ever looked at the ultrasound probe, how it works is that you have a power source that's kind of providing the electricity, and then that electricity starts activating the piezo crystal. And then the piezo crystals start vibrating and then start generating sound wave. And then that sound wave is used in both laboratory ultrasound probe or the medical ultrasound probe. So the one example you're seeing here is the medical ultrasound probe. This one actually relatively use smaller amount of power or electricity compared to the laboratory ultrasound probe because it's a medical use and you don't want to apply too high of a ultrasound wave or the sound wave to human's body and too high of a electricity to human's body. So one example is that sound wave kind of provides this image of fetus, and you can kind of monitor the fetus throughout your pregnancy process. So this is another example where piezoelectric crystal is being used for their daily applications. I'm going to mention a couple more here. So igniter is another application that uses the piezoelectric crystal. So how it works is think of the one that actually doesn't use the spark wheel, the one that actually just uses the button. So what happens for this application is that when you press the button, it presses the piezoelectric crystal, and that generates the electricity, and that electricity is used to create flame for a igniter. The last application I'm going to mention here is a tire pressure monitoring systems. So nowadays, a lot of cars have this monitoring systems for their tires. So if you were to kind of supply power for these sensors through a battery, it's going to just consume so much energy. So what these car manufacturers are now doing is that they use piezoelectric crystal. So when you attach this small, tiny sensor to tire, it's going to constantly move, and then that movement, that stress and that stretch will create a tiny bit of electricity, so it constantly gives feedback as long as you're driving, as long as the wheels running or turning. So with that sensor, the car manufacturers don't have to worry about providing the power to this sensor. Instead, they generate its own power by its movement, and then it just constantly gives you feedback of a tire pressure. So that's the last application I'm going to talk about that uses piezoelectric crystals in our real-world applications. Okay, so how is this piezo crystal manufactured? This is like a typical workflow here. So you have incoming raw materials, and then when you get the first incoming raw materials, you definitely want to monitor your particle size, and then you weigh per formulation, and you start milling and blending. And then after milling, obviously you want to monitor your particle size and to see whether it's appropriate for calcination. And then once you do a calcination, you do milling again, and then at that moment again you want to monitor your particle size, and then finally you kind of spray dry these powders before you pack into this different shape of piezo particle crystals. So obviously, if you look into this slide, there are 4 processes that will involve particle size measurement. And this is very crucial because based on your particle size of these materials, your performance, your packing, and everything gets affected. So it is very crucial to monitor particle size of these piezoelectric powders. So how do you do it? So for our presentation, for our testing, we used a HORIBA LA960-hour laser diffraction unit that uses Mie scattering theory. So how we disperse these particles was we use water with surfactant. For this case, we use 0.1 weight% of sodium pyrophosphate. The refractive index of this piezoelectric particle generally range from 2.32 to 3.22. And refractive index is very important when you measure particle size that's smaller than 50 micron. So it's based on the ISO 13320, the guideline for any laser diffraction technology. So we did pay very close attention to refractive index we used throughout this testing. So let's first look at incoming raw material. So we start with the lead 2 oxide. And if you look at the images there are two images on top. You can see there are some quartz particles that are visibly large. And if we measure that in the LA 960, or when we measure that in the LA 960, we clearly saw bimodal distribution. So at this point, we're not sure whether this is the permanent aggregate or is a loose agglomerate. So one way to determine whether it's a loose agglomerate or the permanent aggregates, we do our own ultrasound study. So what we do is we apply ultrasound for a certain time and see how particle size behaves. So we apply a minute of ultrasound. After that, clearly the coarse peak on the coarser side disappeared, and now it's a unimodal distribution with the median size of about 6 micron. For packing and everything, you want it to be unimodal, and you want it to be relatively narrower in the size distribution. At this point, we wouldn't accept this. 6 micron is still too large, and then if you look at the particle size distribution, it's quite broad, covering from about 500 nanometer up to about 20 microns. So we want it to be a little bit more smaller and then a little bit more tighter. So let's move on to the next raw material, which was lead 4 oxide. And if you look at the distribution, it's a nice unimodal distribution with the median size of 2.6. And at this point, we're happy with the median size and also with the distribution width. So this is ready to move forward with the manufacturing process. Okay, we also measure some other stuff, some other piezoelectric particles, and then let's look at lead zirconate. So if you look at the size, just the size without looking at the graph, you will see the median size about 2.6, which is where we want to be. And then if you look at the distribution between D10 and D9, or the difference between D10 and D90, they're about 3 micron, which is where we want to be. But if you look at the graph here, you also see some sort of bimodal distribution behavior. In this case, we do not want to pack because this fine peak on the finer side, around about 200 nanometer, this can cause some serious problem when we want to pack into a specific shape. So the general rules of thumb for packing is that you want it to be unimodal with the narrow distribution. So anytime you see bimodal distribution, you might want to avoid that. Okay. And the last material that we're going to look at is PZT, also known as lead zirconate titanate. So there are two types, hard and soft. Hard because its dipole or domain is restricted by composition. So it's hard to change its composition, and then it can stand high electrical, high temperature, and mechanical stress. So this is mainly used for some of the things that needs to withstand high temperature and high electricity. So some of the example is welders and ultrasound cleaners, or the laboratory ultrasound probe. And there are also soft PZT materials. Soft because dipole or domain isn't restricted by composition. It has high permittivity, high coupling, high Curie temperature. So it's used in applications when high sensitivity is required. You don't want to you don't want to apply high power or high electricity through this one. So this one is used in about like a medical ultrasound or the gas igniter. Okay. And so we measure both hard and soft PZT on our LA960. As you can see on the graph, hard PZT had a very small distribution, or small size, median size at about 3.1. With a relatively narrower distribution, whereas soft has bimodal distribution. So this indicates two things, or we can assume two things through this application. Is one, maybe soft PZT is easier to break, so you need to be very careful with the ultrasound treatment, amount of time you apply ultrasound. Also, you want to be careful with your milling process and make sure you don't over mill to generate these submicron particles. So those are some of the differences between soft and hard PZT. So the challenge would be hard PZT would be a little bit easier to control the particle size, whereas soft PZT, you need to be even more careful when you process these materials. Okay? So finally, I wanted to show you guys a tool on the LA960. We can do a RI, or refractive index assessment. So based on our assessment, we figured the imaginary index 1 is the best choice for this material. And how do we determine that? If you do our method expert testing for the refractive index, then it plots out 5 different graphs and then 5 different size distribution with the R parameter values. So whatever that gives you the minimum R parameter value is the best value. So if you look at the graph on the right bottom corner, there's an R parameter value graph. And then if you look at it about when you use 1 imaginary or 2 imaginary, it gives the lowest R parameter value, and we went with the 2.2 as a real refractive index and 1 as imaginary index. I want to give out thanks to Wayne Lee of Harris Corp providing general knowledge of this PZT manufacturing process. We learned a lot throughout this process. And if you guys have any questions later on, you can always email us at labinfo@horiba.com. And you can also download this webinar later on. We upload every webinar that we do, and that's going to be on our website. And besides webinars, we also have an entire range of particle characterization analyzers on our website. It's www.horiba.com/us/particle. So if you guys come visit, you will be able to find a lot more information on our website. Look forward to hearing from you guys if you have any questions. Thank you very much for watching. Bye.